This is the video for Quiz 1 from 2023, and what I'll talk about is what we covered, what we tend to expect, and what exactly we're sort of looking at as we sort of test you. I guess that's the best way to put it. So the learning objectives are pretty often or pretty much limited to the particle component of the course, and we tend to look at projectile motion. Coordinate transforms are very important, position, velocity, and acceleration. And sort of parenthetically, we look at unit transformations. And unit transformations are just a way of making sure you're keeping up with all of the expectations of the course. So this is roughly about a month and a half into the course, and this is a pretty consistent expectation. It may change dependent on when the first quiz is offered. So you have a small airplane that's flying horizontally with a speed of 290 kilometers an hour. And you kind of have to expect that at this point, we're going to be looking at things or expecting you to sort of cover or convert that to meters per second. Usually we'll look at something like that. At an altitude of 120 meters above a remote valley, drops an emergency a medical package at point A. So point A is shown right here. Yep, there we go. The package has a parachute which deploys at point B and allows the package to descend vertically at the constant rate of 1.8 meters per second. So the tricky bit in this is recognizing that this is a parabolic path. And we'll use standard projectile motion. And then for the last bit, from B to C, it's going to be a vertical distance. If the drop is designed so that the package is to reach the ground at 39 seconds after release at A, determine the horizontal distance L so that the package hits the target. So the target is down here. Use the axes shown. What is the R theta location of B? Neglect atmospheric resistance from A to B. So you're given 120 meters vertical height. You're given no information about B to C, but you're given that that time for the package to drop has to be a total of 39 seconds. You're also given, of course, gravity, 9.81 meters per second squared. So what you have to do is start to break it up into parts. So you have A, you have B, you have C. You know from A to B, it's going to be standard sort of approach, y equals 1/2 GTB squared. And to fall from position B to C, the height minus y, which is the distance, is the distance to point B. And that's going to be the height minus 1/2 GTB squared. So the package has a speed that you can calculate directly from the delta t from C to B. So from point B down to point C. TC is of course greater than B. And you know what the heights are. So you have one equation to give you everything. So you end up with an expression that looks as 1/2 GTB squared minus package of the speed TB plus package of the T speed times TC minus the height is equal to 0. So putting some numbers in, you know everything right there. And that's it. There you go. Everything's solved. So you can solve for a solution for TB, which is minus 3 seconds or 3.35 seconds. And of course you can't have a negative 3 seconds, and so you end up with 3.375 seconds. So from that you end up with a parachute height of 64.128 meters. So of course that means that you have roughly 56 meters of fall from point A to point B. The length that you were asked to solve for, which is the length here, is just the time it takes, because That's just going to be the time from A to B, and it's going to be 3.375 seconds. And the total time is equal to 271.9 meters, or length is 271.9 meters. So for this one, part of the problem, you're just doing a coordinate transform. And you recognize that what you have is a coordinate transform that allows you to say this distance right here, which is YBC, and this distance right here, which is L. Not really well done, but okay. And from that, you can calculate the distance R, which is that hypotenuse, and theta, which is just going to be the angle that hypotenuse makes with the horizontal. So going forward, you have L, YBC, you get 279.3 meters, theta, which is the inverse tan of YBC over L, and you get 13.3 degrees. One thing that I mention in all of my lecture sections is that there is a preponderance of questions that deal with baseballs and golf in dynamics. And so you have a characterization, I suspect, of what MIE100 instructors at various universities do in their off time. So here is a typical projectile problem, in the sense that it's an MIE100 instructor out playing golf, hits the golf ball with a initial velocity of v naught equals 50 meters per second and theta naught of 29.5 degrees. The trick here is the introduction of a wind resistance, which is a deceleration in x, because most of the problems that you've done so far have told you there is no deceleration. And you're then asked to find at one time, the r theta, r dot theta dot, and r double dot theta double dot. So again, here's an xy coordinate. You have an acceleration as normal in the y direction of g, but here you have a new acceleration, which is negative 1.3 meters per second. And you have a coordinate system that defines it. You're given a drawing that shows you the position and direction of the term. So theta 29.5 degrees, v naught, which is 50 meters per second. When you do these problems, draw it out. And I can't stress that enough. I won't stop stressing it, so you're going to be stuck listening to videos. Maybe you skip over this bit, but draw the directions. And you'll notice that I have put in a Vx and a Vy. I have extended out where I expect this golf ball to be at that instant, and that becomes my r and theta coordinates. So that's how I'm going to do my transformation. So I need to know this theta of position at that time, which, not inconsequently, is the same as this one. So AX is minus 1.3 meters per second squared. You have the x plot, and because of the way I wrote it, I can just leave that as a positive, so that it becomes negative here, and g is same thing. You just sort of write it that way. Put in the terms, x position, y position. So the x position and y position are sort of determined this way. So x pause, y pause, and you end up with x position, y position, r equals, and the theta at that time of 24.4 degrees. So remember, you started at 29 degrees, you're now at 24.4 degrees. We still are going to stay with the same position in time, but now put in all the terms. So now we put in all the velocities, so we get Vx, Vy, standard projectile motion expressions. Vr is given as Vx cos theta pause, Vy sine theta pause. So it's important that as you're looking at this, yeah, you know what, that makes sense. Vr is going in this direction, so it's going to have a component in the x direction. It will have a component in y. Both of those will be sort of acting in this positive r direction. So in this positive r direction. So they're both positive values. V theta, on the other hand, is going to have a component of r theta dot, which is going to be Vy cos theta. So Vy is acting in the positive direction. but the component of x is actually going to act along this direction. So it's going to be negative. And so when you do all of the calculations for those terms, you end up with a negative value here. And so the important thing is to calculate that. And to find theta dot, you just use definition. So theta dot is equal to v theta is equal to r theta dot. And so theta dot is equal to v theta over r. Put the numbers in, get the values, and there you go. Other thing that's important, and I didn't stress it previously, units. Units, units, units. This is important. You need to do this all the way through. But again, sort of stepping on the soapbox here, make sure that you draw the diagram. Finally, we have the last part of the question, which is the acceleration in r and theta. And again, you'll notice that the acceleration r is going to be in the negative sense. So I have a g acting downward in y. I have an x which is acting in this direction. So to align in the r direction, it's going to go in this direction, which is clearly a negative value. So both of those are negative. As for the theta components, both of the theta components also act in the negative theta direction, which is a clockwise rotation. So putting in the numbers, using the definition, r double dot minus r theta dot squared equals AR. We can calculate AR from geometry, right here, A theta from geometry, and then substitute in definition. And what we need to know are these terms, and the previous part of the problem we solved for these. So we find acceleration, r acceleration theta, negative, negative, which kind of makes sense. We kind of expect things to decrease in speed or velocity. And we find r double dot and r theta and theta double dot from this. And it's a very small number in theta double dot, and it's a pretty significant number in r double dot. Same thing as before, you kind of have to recognize that the magnitudes of the individual magnitudes of each component is not going to be the same. Total magnitude is the same. And so in order to sort of extract out AR, I need both components of AX and AY, G in this case, and an A theta, same thing. And I need to know what I'm looking at, which is why drawing this out is actually a valuable tool to solve these problems. For the rotation matrices, there was also a comment by one of the TAs, Coder Jobber, who suggested using a rotation approach, and I thought this was a great way to solve these problems. Basically, recognize what you have and then just put the terms in. So cos theta pos, sine theta position, so minus sine theta, and you have Vx, Vy, and Ax, Ay. And you end up with exactly the same result. And as long as you do the calculation right, you'll be fine. There you go. I'm going to stress more as we go over the next exam and the next exam, or the final exam. So we have a midterm and a final exam that follow this. What's happening with the dynamic concept inventory? At this point in the course, we're really laying down some foundational ideas. How do you do coordinates? How do you use some of these ideas in terms of kinematics, primarily at this point? Coordinate transforms become very important and are crucial for the second part of the course, where we start to deal with rigid bodies, which become very complex in terms of their motion. And ultimately, you really need to know the kinematic terms in projectile motion. So strongly suggest, if you can, to spend the time to look at all of this and not just look at the old exam videos or the old exam solutions, but also to look at other sorts of resources. So again, there are a number of practice problems for you to try. There's a number of other material that I think might be helpful to you. Thank you very much, and we'll talk later.